All right, so today we will do a question from mechanics, class 11th physics. For those of you who are interested in learning about this, the topic is finding the reading of the weighing scale when the weighing scale is inside the lift. So you can see I'm drawing a man who's standing on the weighing scale inside a lift, or what they call as elevator. Now the man is experiencing you know force from acceleration due to gravity. The earth pulls the man, and the elevator has what you call as an acceleration. The acceleration of the elevator can be upwards, downwards, and our aim is to find the reading of the weighing scale when the lift is going upwards, that is accelerating, the lift or the elevator is going downwards, accelerating. And in the third scenario, what we plan to do is to find the reading of the weighing scale when the lift has a constant velocity. All right, so I hope the problem statement is clear to you. We are talking about a man standing on the weighing scale. The weighing scale reading is to be noted. The conditions are that the lift is accelerating upwards. The second situation we need to find answer for is when the lift is going downwards. And then of course, we will also do a preliminary, maybe later, a situation where the lift is moving with a constant velocity. So our aim is to find this reading, and we will understand today how to find this reading of the weighing scale. All right, I hope this is making sense to you. Very important problem. In this question, the man's mass is given to be 70 kgs, right? So the mass of the man is already known to us, and let's try and solve the question for the initial situation also, where which is a situation third actually. We will do it in the last, although I'm writing this as an initial situation when the velocity is constant. I think we've already covered this point. Now let's understand how to do the reading of the scale with the help of a free body diagram. It is very important to draw a diagram in mechanics. Without the help of a diagram, you cannot do this. This is your scale, and the man is standing on it. This is a normal scenario. I will not draw a elevator or a lift. Now, this man, when he stands on the weighing scale, is attracted by Earth downwards, right? So gravity is going to attract this man downward, and this gravity, the man is attracted by a force which is mg. So this is a situation like in your house, right, which we call as a ground situation. This is not an elevator situation. So how much force is experienced by the scale when you stand on the scale? If you're 70 kgs, 700 newtons, right? Straight away I'm taking g to be 10 meters per second square. So I hope the scenario is clear to you. This is the force being experienced by the scale because the man is getting pulled down due to acceleration of the gravity. I hope this makes sense to you, right? We're talking about a normal scenario. We're not trying to solve the problem right now. We're just doing a free body diagram. So now I've drawn an arrow which shows the force being exerted on the weighing scale by the man, right? This is 770 g into 70 into 10. So you know what is the attractive force on the weighing scale. Now what happens if the scale experiences a force? Newton's third law says that the man should also experience a force back coming from the weighing scale. The scale pushes back on the man. So if you see the arrow on the left hand side, it's a pushback from the weighing scale to the man, and the man experiences what is normally called as a normal reaction. So the normal reaction when you're on the ground is how much? It is same as the mg. So n is equal to mg. Now here is a difference. The normal reaction, which you call as a normal reaction in the case of weighing scale, I'm going to call it as a scale force. The scale force is the force coming from the scale back to the man, and it is same as the weight of the man, which is the force being exerted by the man on the weighing scale, and a pushback which comes from the scale to the man is called as the scale force. So I hope the concept of scale force is clear to you. It is nothing but the normal reaction. Now, what is the beauty? The beauty is that the scale force is the reading of the scale, and that is why I've just highlighted now. The scale force, which we just calculated as the pushback from coming from the scale to the man as a normal reaction, is the reading of the scale. This concept, if you get, you can solve this problem by knowledge of mechanics now, right? This is not clear to the student. What is getting measured? It's a pushback from the scale, the normal reaction which is getting measured on the ground and also when you're inside the lift. In both the scenarios, this is what gets covered. There is absolutely no difference. Now let's apply the concept of scale force, the force which is coming from the scale to the man in the first scenario where the acceleration is 2 meter per second square. The lift is going up, so the scale is also accelerating up. I'm drawing the free body diagram. Now you already know that the scale, because the man is standing on the scale itself, the scale pushes back with 700 newtons. Additionally, right, so back the additional force is coming from the scale. The scale is also accelerating upwards with an acceleration of 2 meter per second square, and therefore the scale exerts an extra force on the man because of its acceleration. So the extra force on the man coming from the scale is 140 newtons. Therefore, the total scale force on the man is now 2. One, because of the normal reaction, and second, because of the accelerating scale, which is an extra scale force coming of 140 newtons. And therefore, the total weight experienced is 840 newtons. So if you're going up, you are likely to feel heavier when you're going up and the lift is accelerating up. So you can have a question like this. If you're going up, accelerating, will you feel lighter? Will you feel heavier? You will feel heavier because the additional force of 140 newtons is coming on you and you're accelerating up. I hope this is making sense to you. Part 1, lift is accelerating upwards. What will be the reading of the scale? The reading of the scale will be 840 newtons. I'm repeating myself to ensure that this point gets hammered in your mind very, very clearly, because this is where most of the students falter in their understanding. It's a very important point, very different way of thinking about the weight concept itself, the reading on the weighing scale. Let's talk about situation number 2, where you have the lift or elevator which is going down with an acceleration of 2 meter per second square. Now the normal reaction is 700 newtons, which is equal to the pushback coming from the scale. Additionally, since you're going down, the man is experiencing a downward force coming from the scale of 140 newtons, right? This is a manifestation or the appearance of the acceleration of the lift on the man. The weighing scale is now putting a reverse 140 Newton force on the man. The scale force, because of the acceleration, is downward. Now the man feels lighter, and the net weight of the man, because the lift is going down, at the rate of 2 meter per second square, will be 700 minus 140 is equal to 560 newtons. I hope this is also clear in your mind as to, in the part 2, what is the net weight of the man when you're accelerating downwards. 560 newtons. So you will feel lighter. And remember, if you're in a lift which is a high speed lift in Manhattan or some place, it's going fast very down, you do have so to say a feeling in your stomach, right? And that's like being without gravity, right? You feel weightlessness, right? That's feeling light. That is what is being referred to. So I hope the situation number 2, accelerate downwards, is also clear in your mind when it comes to solving this problem. Let's proceed to the situation number 3, which is when the lift is at constant velocity. Now the lift has no velocity, and therefore the scale too has no velocity at all. Why will the scale have any acceleration if there is no change in the velocity? The velocity is constant, and therefore there is no accelerating elevator, and therefore there is no accelerating scale, and therefore there is no additional force which is coming from the scale on the man by virtue of any acceleration. So therefore, the reading on the scale still remains 700 Newton, which is same as the scale force due to normal reaction. So scale force has sources now. Scale force due to acceleration, scale force due to acceleration downward. The scale force could be because of no acceleration, constant velocity. So scale force has to be looked at in these numericals. They're very easy to solve. Please don't get scared if you get a similar question in your examination. These are straightforward, simple questions to solve. You don't have to worry at all when it comes to solving them. Now, this is what you need to do. You need to analyze one more thing in your mind, which is what happens in the scenarios where the lift is decelerating, right? Now, the lift is going up, but it is decelerating. The lift is going down, but decelerating. How would you solve these problems? Knowing fully well that you understand the scale force pretty well now. Do not be afraid of minus sign. Just think logically. What type of force would minus 2 meter per second square have on the man as coming from the scale? And then analyze and think about it. Think about the direction of the elevator. I'm giving you a challenge problem. Think about it. If you get this right, probably, and I will make a video later after some time. I'll give you some time to think about it. Let this be a competitive situation where you need to apply yourself and think. And then I'm going to put a video where I will explain what happens when you have minus 2 meter per second square upward and downward. How is the weight impacted? But it's a straightforward question. I'm just trying to tease you a bit, giving you some challenge to work on, trying to motivate you. Have a look at this over and over again and understand the concept of scale force very well, and you're good to go. I hope this made sense to you today. Thank you very much. Don't forget to subscribe. Thank you.